Hello everyone and welcome to this TA session, which is the week 7 TA session for the course of Physics of Materials, which is an NPTEL course. The instructor for this course is Professor Pratap Haridas from IITM, and my name is Mohammad Tahseen. I'm the TA for this course. Now, this TA session was actually supposed to happen yesterday, but because of my travel, I could not conduct the session as per the schedule. So I'm conducting this session today, and I guess the information had been provided to all students. It had been communicated that the TA session will be delayed by 1 day. And so for next week as well, because of my travel, the TA session would be conducted on the next Saturday instead of the the next Sunday instead of the next Saturday. So let me start this session by presenting my other screen as well. So here is a summary of the things that we did in the last TA session. So we started with some numerical examples, which were inspired by the discussion we had in the preceding week and even before that. So, so the first let's go through them briefly so as to recall what the discussion that we have been having. So roughly, to summarize where we are at this point in the course is we have been trying to. So first, we introduced the Drude model as a model to basically understand the origin of electrical conductivity and thermal conductivity of solids, and we introduced this Drude model, which follows the classical mechanics framework, right? So the particles in this case, which are the electrons, so those electrons are assumed to be classical particles in the Drude model. And we found that because of this assumption, the particles being classical, we run into some problems. The Drude model over-predicts some quantities of interest and it under-predicts some other quantities. So in order to correct these shortcomings of this model, we introduced a new model which is called the Drude-Sommerfeld model. And the difference between the two models is that this new Drude-Sommerfeld model, it treats the electrons as quantum mechanical particles instead of as compared to the classical particles, which is done in the Drude model. And accordingly, the statistics which describes uh, the configuration of these particles is governed by the Fermi-Dirac statistics as compared to the Maxwell-Boltzmann statistics in the case of Drude model. So that is the main difference, and we are going to continue this discussion today. But just before that, I briefly want to recall the things that we discussed last time. So first we looked at this graph. This is actually the energy plotted as against the number of states that are being filled, and this graph, this plot comes from Maxwell-Boltzmann statistics as done in the Drude model. So what we find here is that as we increase temperature, so the temperature shown in the pink here, T2, it's greater than T1. right? So if we look at how the distribution of electrons changes inside a solid as the temperature increases, it shows us that the states with lower energy, they are filled less as we increase the temperature, and the states which have a higher energy, they get filled up more. And furthermore, the other thing it shows us is that all the electrons, all the classical particles that are present in the system, they uh, they change their state as the temperature changes, right? Or in fact, the all the particles change their state. That's why the temperature changes. That's how it is able to maintain equilibrium with its surroundings, right? So this is a typical feature of Maxwell-Boltzmann statistics. And then we so these are actually the problem set that we did last time, and I'm just briefly recollecting the main points here. So this is actually the first experiment um, which contradicts which leads to the failure of classical mechanics in explaining uh, any natural phenomena. And this is the what we call the black body radiation, the plot shown here. And we see that the Rayleigh-Jeans law, which is again based on the Maxwell-Boltzmann statistics that we saw above. So this Rayleigh-Jeans law is not able to predict the black body behavior or explain the black body behavior in across all regimes. So it only does that in the high wavelength region, right? Or this yeah, when the wavelength of the emitting the radiation being emitted is quite high. So or equivalently, we could say that the frequency is low. So this is the low frequency region where the Rayleigh-Jeans law or the classical mechanics is able to explain or predict the natural phenomena. But as the wavelength gets lower or the frequency gets higher, this Rayleigh-Jeans law fails to provide an explanation to this black body behavior. And this region where the where the failure of Rayleigh-Jeans law happens, it's called the ultraviolet catastrophe. And this was one of the reasons that led to the emergence of quantum mechanics. So that's that. So this experiment holds a very high importance in the history of events. Okay, and later we saw that the photoelectric effect was again it was known, the experiment was known, the experimental happening or the finding that was known, but there was no explanation based on classical mechanics as to why this happens. And this was done by Einstein, who figured out a way to explain this photoelectric effect using the already established theory of Max Planck. And so there was one more famous experiment done in 1927, which is called the Davison and Germer experiment. And in this experiment, this was the first experiment which established the wave behavior of electrons. Before this experiment, electrons were assumed to be particles, even quantum mechanical particles, but as per the de Broglie's hypothesis that matter can behave both as a wave as well as a particle at the same time. So this experiment was the first experiment done in this line of work to establish the wave behavior of electrons. And the successful diffraction of electron beams was observed in this experiment. And then we started looking into the Drude-Sommerfeld model, which is based on all these quantum mechanical phenomena. One phenomena in particular, actually, but that encapsulates all other assumptions of the quantum mechanics. Okay, so we started with some assumptions that Drude-Sommerfeld model, as is the case with Drude model, it's also a free electron model. It assumes the electrons to be to move around in a conductor or in a solid in such a way that they move freely. They are not bound to any potential or anything. And the difference from the Drude model lies in the second point, which is that this model, the Drude-Sommerfeld model, it applies quantum mechanical principles to the Drude model, and in particular it applies the Pauli's exclusion principle, and it assumes that the potential is constant within the metal, and electrons as such, because they are now quantum mechanical particles, they are identical and indistinguishable particles, and behavior of the large collection of such electrons, it's governed by Fermi-Dirac statistics as opposed to the Maxwell-Boltzmann statistics in case of Drude model. Right? And so if we have energy levels in any system, if we have energy levels E0, E1, E2 up to ER, now there's a concept of number of states which was not there in the original Drude model, and this is a consequence of the Pauli's exclusion principle, that at a particular energy level there are only a particular maximum number of states that I can fill, and I cannot go beyond that. While as if we assume the particles to be classical particles, there is no such limit. We can fill any energy state with an infinite number of particles. And now the distribution is represented, distribution of particles inside these states, that is represented by the letter n. So n0, n1, n2 and so on up to nr, these are the corresponding particles present in these S0 number of states. Right? So in each case ni should be less or equal to si for I equal to 1, for I runs from 1 to r. Right? Because the number of particles in any state, they cannot exceed the number of states available at that energy level. Okay, so what our goal was last time, it was to find the most probable distribution, right? This distribution, which is assumed random here, we have to find the distribution that maximizes the configurational entropy, right, of the system. So that state would correspond, or that distribution would correspond to the what we call the most probable state of the system. So we did I'm not going to go into much detail here, but so let me go to the formula directly and try to explain from there. So this is the formula that we obtained. Okay, that F here is the probability of occupancy of the energy level EI, right? And we found that this expression for this F of EI is equal to 1 over 1 plus EI minus EF over KT, right? And EF here is the Fermi energy, and EI is the energy of any state that I am interested in, right? So this F of EI gives me the probability of occupancy of that energy level, right? And if we look at now, if we plot this function, we find that at absolute zero temperature, when temperature is 0 Kelvin, the probability of occupancy of every energy state till the Fermi energy, right? So Fermi energy is the highest occupied energy level at 0 Kelvin, right? So we found that at EF, which is the at absolute zero temperature, every energy level up to the EF, which is the Fermi energy, that is occupied, right? And all the energy levels above EF, these are completely vacant. But as the temperature increases, if we go from T0 to T1 to T2, where the temperatures are increasing in ascending order, so we find that the distribution changes occur just around this Fermi level region, right? So the region around the Fermi level, only that undergoes a change in distribution, or the probability of occupancy changes just for the energy levels around this Fermi energy. While as in case of classical mechanics or the Maxwell-Boltzmann statistics, we find that the change happens everywhere, right? So this plot, it corresponds to the Maxwell-Boltzmann distribution. We see that even the energy levels which are far lower than the corresponding to this point, even they undergo a change of distribution. So this is the main difference between the two statistics, and why they prefer, why they basically uh, why they lead to different results for certain quantities like thermal conductivity, right? So with this discussion, let's begin today's session. So the course name is Physics of okay. So what I want to discuss today is the concept of anisotropy in solids, and anisotropy and periodic potentials. That's the topic for today. So it is motivated by the fact that if we consider Rood models, and so it predicts a value of let's say thermal conductivity that we saw, or even the Rood Sommerfeld model, but there is no indication, or there is no discussion of a particular direction inside a solid that we assume while deriving these models, right? So but in if we do the actual experiments, we find that the properties of a solid may change depending on the direction we are interested in. Okay, so for example, let's take a very simple example of a mm, oh, I can't think of anything. Okay, so the example that was discussed by Professor Haridas in the lectures, that was that of the graphite, right? So if we look at graphite, we know the structure of graphite is something like this, right? So this is a hexagonal carbon structure, and when you stack these several layers on top of each other, that is the structure of graphite, right? And if you measure thermal conductivity first in this region, or even the electrical conductivity in this direction, right? And if you measure the thermal conductivity in this direction, so these are uh, quite different. Okay, probably I should use a different color here. Right? So these are quite different values of thermal conductivity, or let me just write conductivity along this direction. right? And this kind of behavior is not special to graphite. In fact, if you look at most of the materials that we encounter in, for example, metallurgical engineering or uh, mechanical engineering, they tend to possess this anisotropy. Okay, so I just remembered of an example, which is a famous example for this anisotropic behavior. That is that of wood, right? So if you take this wood, for example, a log of a tree, right, in that form. So and say let's say this is the log of the wood, something like this. So if you do its mechanical testing first in this way and then along this way, you will find that wood is much stronger in this orientation, right? The values of elastic modulus and other such quantifiers or shear modulus that you would find along this direction. Okay, this is the direction of the fibers of the wood. This would be much higher than corresponding to the transverse direction. Or even better example would be compressed wood or plywood, right? So basically a plywood is a composite, right? So how it's made is you have to, so roughly I'm drawing this picture for any composite. Let's say this is any general composite. You have a matrix, and inside matrix you have some fibers. Or for example, say these are carbon nanotubes, for example, in some matrix, right? So now once you make this material, then so this is the direction of fibers, right? And if you let's say apply a load in this direction, it would have much higher tensile properties than as compared to this direction, right? And sometimes this is intentional. We want to design materials which are anisotropic based on our needs, and this uh, whole area of composites that offers us a nice way of doing it. So we can achieve, or we can, for example, the one layer of composite can be in this direction, and the next set of fibers we can lay at some angle, let's say 30-degree angle to this, right? So this generates an entirely new set of properties, right? So the point is that materials are anisotropic, right? And if we have some model that predicts the behavior or that predicts the certain quantities, then it should also be able to predict the anisotropy behavior related to that quantity. For example, if conductivity is high in one direction and low in one direction, the model should be capable of accounting, taking that variation into account, and it should offer us a means to understand why there is a difference between thermal conductivity properties or any property along different directions of a solid. Now, the one advantage of knowing this could be that we could, for example, we could find out which is the direction in which certain property is maximized, or which is the property in which certain direction is minimized, right? These considerations and the knowledge of such maximization and minimization of properties along certain directions, that's of great use to let's say any people who want to design a technology, right? So for example, we know that if we have concrete, right? Let's say I have a concrete bar. Concrete. Now, Okay. So does anyone know how concrete fails? What kind of loading does concrete fail under quickly? I think there is only one member present. So Anto, do you have any idea how concrete fails?
No, sir.
Okay. So let me tell you. So concrete is designed in such a way that concrete is extremely durable under compression, right? So if you compress it, it can take high amount of compressive loads. That's why the pillars of our houses, they are made of concrete, right? And there is a vertical load which is due to the, let's say, the floor or a roof, right? All the load of a roof that falls, that applies a compressive load on our concrete walls, right? Walls as well as pillars. But what concrete is weak is in tension, right? So concrete is weak in tension. So if we were to apply a pulling force on concrete bar or slab, we would find that it will fail at much lower loads than what it can sustain under compression, right? And that failure actually happens. Okay, so that failure happens along a shear, right? So for example, say this is, let's say that I am applying a tensile force T on a concrete bar, right? So if we take a section which is at 45 degrees to this applied load, right? Let's say this is 45 degrees. The plane of the concrete inside the bar, this plane actually, the value of shear stress here is maximized in this plane. Okay, so this is the plane of maximum shear stress. Right? And first cracks in concrete that would appear along 45 degrees to this load, right? So this is seen even in, for example, if we look at cracks in concrete, mostly they would occur along 45 degrees, right, to the loading axis. So this knowledge of how the failure happens, or in this case, or in general, how a property varies along the different directions inside a solid, right? That is of high importance to engineers, designers, and people working in technology, right? So so the point is that if any model is claiming to explain the behavior of a solid, then it should explain this behavior as well, right? This anisotropic behavior. So let's put some words to it. Anisotropy. So anisotropy means the variation of properties along different directions in a material. Now the question is, why does this anisotropy happen? Why does it occur? Right? Why are materials anisotropic? So the answer is that it stems from the structure, the basic structure in which the materials construct themselves, right? If we look at the atomic structure, for example, let's say this is some solid, say copper. Let's say this is the structure of copper, right? Actually, copper has a different structure, but just for the argument's sake, let's say this is the, or let me make the spacing lesser in one direction and more in one direction. right? So let's say copper or some imaginary material, it crystallizes in this form, that this is its crystal structure, right? So if we take a unit cell of this crystal structure, this would be its unit cell, right? And what we see in this unit cell is this bond length, right? This bond length is greater than this bond length, right? And this means that the way that this particle and this particle interacts is different from the way this particle and this particle interacts. So if there is some property which, because ultimately all the properties that are shown by solids come from interactions between different species, right? So if we measure some property in this direction and measure the same property in this direction, they would be different, right? Because the interactions happening at the atomic scale are different. So this is the basis of anisotropy present in materials, and mostly solids are most anisotropic phases of matter compared to liquids and gases, right? And the reason is because solids are ordered; they are mostly ordered species, and so this effect dominates, right? So, so this is about anisotropy, and yes, so now we will specialize to one uh, topic, which is anisotropy in crystalline solids. Crystalline solids. Okay. So we can consider the case of metals for this discussion, right? We can keep metals in our mind. So what happens is, so if we take some patch of a metal and look at it under the microscope, right? What do we find? We find that there are grains present inside. Grains are present inside the material, right? And we can see them through microscope, not through the naked eyes, right? So the grains would be something like this. Yeah, something like this. Okay, so this would be the grain structure. So what are these grains basically? Inside the grains, there are regions, or grains themselves, it could be called as the regions, which have a regular crystal structure, right? So if you look at inside one grain, the situation is something like this. So it has a very particular arrangement of atoms, right? So something like this. But if we look at a different grain, a neighboring grain, the same structure gets reoriented, right? So for example, in this grain, the structure could be something like this. So it is the same crystal structure, same arrangement, but just reoriented, okay, rotated with respect to the crystal structure in the other brain. And all these different reorientations, they generate our material, right? So now one could ask, why does this reorientation happen, right? Does anyone know the answer? For metallic solids, why are there grains present inside instead of no grains? The entire material could have been like this or entirely like this. Why do we see grains in the first place? Does anyone know? So it's because of solidification, right? This is the usual case in which uh, grains are formed, right? So different solidification or nucleation fronts, right? So what happens is when for example we have metal in the molten state, right? So and we are cooling it, the solidification process, it does not happen at a single point, right? It happens across multiple points inside the material. And as we keep cooling the material, those solidification fronts keep growing from those points. And this process is called nucleation, right? Nucleation of a solid. And then we have different nuclei located around the material. And when they grow and they interact with each other, they grow in totally different directions, right? For example, if we have a piece of solid which is growing here and so a piece of solid which is growing here, right? They wouldn't know that which orientation. So this piece of solid, it wouldn't know what configuration or what orientation is this piece growing in, right? So they grow in their own natural, not natural, in random orientations, and when they interact with each other, then there's a competition, right? Basically, there are stresses, and that's why the grain boundaries, these are regions of high stress, and there is no order here, right? Along the grain boundaries, there is no order. Uh, uh, the material is not ordered anymore, and these grain boundaries are regions of high energy, high strain energy, as compared to the lattice. Okay, so that's how grain boundaries form. And now the question is that if, okay, we can ask the same question again that we asked here in this discussion. If we measure the property along this direction and this direction, we argued that they would be different because of the crystal structure, right? Now what happens in this case? What if I measure some property in this direction? Let me draw the directions. Let's say this direction, and then there is this direction. Okay, so if I measure the properties along these directions, what do I expect? Now I know for this material, or the material is the same. I know for this orientation how the results would look like, right? Uh, but what about this? Because now whatever device I am going to load, right? For example, let's say I'm measuring Young's modulus. So I would have some kind of a displacement sensor, not a sensor, but a displacement fixture here and here, right? And I'll try to strain the material along this direction and this direction, right? And suppose I'm measuring stress as I'm doing this. So what stress would that reflect? Would that be of grain 1 or grain 2 or grain 3, right? So it would be an average response from the material. Okay, so let's write these. So such materials, first point is that such materials are called polycrystalline, okay, in which you have grains. So polycrystalline materials have grains inside them, right? That's one point. The second point is polycrystalline materials show a response which is an average from the constituent grains. So what does that mean? That means if we figure out some property of a polycrystalline material, it's an average response of its all its grains considered, right? We cannot say that this corresponds to one orientation or the other orientation, right? So all the orientations in average they show on average they display this behavior. So that leads to an interesting observation. Uh, so yeah, so the thing is, now if we have, so let's say each grain or each crystal orientation shows a particular kind of anisotropic effect. Now what if we had, let's say, one grain is in this direction, right, and its unit cell is something like this. Okay, this is bad. Let's say its unit cell is something like this, right, where the longer side is in this direction and the shorter side is in this direction. Okay, and what in the neighboring, now this is one grain, let's say this is one grain, right, and all the cells or all the crystal structure is oriented in this direction. Now what if I have a neighboring grain right, I have a neighboring grain in which the situation is just the opposite. Something like this. Okay, yeah. So in grain 1, let's say this is grain 1 and grain 2. In grain 1 the longer side was along this direction, and in grain 2 in the same direction we have the shorter side, and the same thing happens in this direction as well. Let's say in this direction we had smaller side here, the smaller lattice length along this direction in grain 1. Now in grain 2 we have the longer side this in this direction, and we already said that these two are similar, they are just reorientations of each other. Now in such a case, if I am to measure the properties, what do I expect? I expect that this behavior will be exactly cancelled out by this behavior, right? Let's say these grains are very small, and so they don't it doesn't recognize that whether the load is being applied on one grain or second grain, right? It just applies a load on average on the material. But the internal structuring of material is such that these two effects, they cancel each out. They can cancel each other out, right? The orientation of our grains is such that any anisotropic effects, right? So if all the material were to be in this configuration, there would be anisotropy in the material. Now because there is another grain which is countering this effect, right, which has an opposite anisotropic effect, I would assume that this anisotropic effect would be cancelled altogether. And this is what happens actually. So if we have a lot of grains, right, or in other words, if the grain size is fine, right, then anisotropy is internally cancelled. Okay, and what we have is giving rise to an isotropic solid. Okay. On the other hand, if the grain size is coarse, it does not cancel the effect each other uh, as in the previous case. So it leads to anisotropy. Right? So we could have some supporting figures like this. Let's say this is my material 1 and this is material 2. And in material 1, the grains are really small, right? This is the grain structure. So it's of this length scale, right? And in material 2, let's say the grains are like this. Right? So this structure we call fine. We call it fine, okay? The grain structure is fine, and here the grain structure is coarse. Now when we have a fine structure, it makes sure that whatever grain I choose, let's say I pick this grain, okay? If the structure is fine, I can say that there would exist another grain in the material which has opposite orientation to this one, right? Because if there are so many grains, there would be one grain which would be cancelling its effect. But that's not true if the grain structure is coarse. If we have only a few grains, it might be possible that no grain is cancelling any other grain's effect, right? So that's why if we have a fine grain structure, it leads to isotropic behavior, right? And if we have a coarse grain structure, it leads to anisotropic behavior. And this is, for example, in metallurgical industry. Right? For example, if we are working with steels, we try to have a fine structure, fine grain structure, right? For structural steel, okay? We don't want that, for example, if some mason is holding a bar this way and another mason is holding the bar this way, that should cause a structural failure, right? So we try to ensure in such cases that our material behaves in an isotropic manner. Okay, so that's about anisotropy. So the point is that uh, anisotropy, the bottom line of this discussion is that uh, anisotropy is an inherent property of solid materials, and anisotropy stems from crystal structure, right? Because the unit cell itself is not symmetric in its two directions or three directions or how many ever directions there are inside solid, right? And it's basically the structure, the making up of the material itself that anisotropy comes into picture. Okay, the packing, or yeah, the exact word is packing. The packing of solids is different in different directions, and this leads to anisotropy. Okay, so that's point number one. The point number two is the bigger discussion that we are having, is that any model which aims to explain material properties, explain the physics behind any particular experiment, right? That should predict, or that should explain the presence of anisotropy inside a material, right? So these are the two points, the bigger that clear the bigger picture, right? So now what we want to do is, so how do we explain, or how do we basically encode this information that there's a difference of uh, packing in different directions, right? So here we start a new heading, which I call the periodic potential in a crystalline solid. Okay. So roughly the idea is that inside a material, inside a solid material, a crystalline material, once we know that the packing is different, it means let's say, to simplify it, the the unit length after which every atom occurs, right? That is different in different directions. So in direction one, maybe after, let's say, 10 centimeters, there's another atom, and in this direction, there is the another atom is at a distance of 5 centimeters, right? So how do I basically encode this information into a material, into a model, right? So first we have to look at what this kind of periodic arrangement does to a material. Okay, so let's say this is a positive kernel inside the material, an atom which has lost one electron to the sea of electrons. Okay, so let's say this is the, and similarly as before, let's say this is the crystal structure. Okay, and the unit cell size in this case, we can see that the unit cell itself reflects that there should be some kind of asymmetric behavior, anisotropic behavior in the material, right? So but then the kind of properties that we are interested in, right, the properties of conductivity, right, electronic conductivity or thermal conductivity. So what happens is those properties are a consequence of electrons moving in these materials, right? So there are electrons, the free sea of electrons, right? So there are electrons moving around in the conductor. And what happens is these electrons are charged, right? They are negatively charged. So let me call it minus Q, okay? And these are positive, these ions, they are positively charged, right? So there is a potential energy difference between in this setting, in this system, right? If an electron moves in this direction, it experiences a different potential because of the location of these ions, right? They are at a further distance than as compared in this direction. So in this direction, there would be a different kind of electric potential, electrostatic potential experienced by this electron than when compared to the electrostatic potential computed in this direction. And this electrostatic potential is the reason, or this is a consequence of this packing, different packing in different directions, right? So if we want to have this the effect of packing, if we want to reflect the effect of packing onto certain properties, we have to consider the difference in electrostatic potential that is presented in these like that is presented by the crystal structure itself, right? So for example, let's say this is horizontal direction, let me call it H, and let's say this is some inclined direction, I call it I. Okay, so along H, if we look at this, so let me draw the positions of ions first by black dots. So something situation is something like this. Okay, this is the H direction. Now, so yeah, now there are positive charges present at these locations, right? And they would create a field of their own. And our electrons, the sea of electrons, which are floating around in the neighboring space, they have a negative charge. Okay, and there will be so both would actually have a field which is given by field would be given by, so field is given by E, electrostatic field, that would be sorry, 1 by 4 pi epsilon naught q1 q2. Now in this case they are both equal, divided by r square, and the sign would be, so this is actually the expression for force, right? And if we want to have the expression for field, we have to divide by one charge, right, plus or minus, right? So this would be the electric field produced by the ions as well as the electron. Okay, the difference is that if we are considering the field due to these ions, it would be plus, and if we are considering the field due to electrons, it would be minus, right? So but then we have a situation in which we have interacting fields uh, in the space, right, where these atoms are arranged. So what happens is we get a field of this type. Once these fields interact with each other, the situation is something like this. Okay, so if I am plotting potential energy on this side and the position on this side, this position, so I have a so now when the electron is at infinity, in that case the potential energy of the system is 0, right? So it would be very close to 0, and as it gets closer to the positive core, there's a build-up of negative potential energy in the system, right? So something like this, the potential would drop off as we get closer, right? And similarly, on the opposite side, yeah, so on this side we would have the exact same situation, right? So this is the left end of the solid, this is the left end of the material, and this is the right end of the material. Now an electron which is coming on from infinity, that would experience this kind of a potential energy, and similarly the electron which is coming on from infinity, the potential energy of the whole system would vary like this, right? It would become negative as it gets closer to the positive core. But in between, what happens in between, right? So in between, the situation is actually similar. There would be contribution from this core as well as this core, right? And similarly this core as well as this core. So but effectively it produces a potential of this form, right? Let me get rid of this, something like this. So this is the effective potential now, right? These are actually a little extended. Okay, so this is how the potential looks like inside a material, and we can see that it's periodic, right? And this periodicity comes from the periodicity of atoms itself. Now what are these lines? So actually the thing is that these two would somewhere they would meet, right? Down below somewhere these two lines would meet, but we do not know exactly where, and it's not even very important to us to know where they would meet. The only consideration is that they would meet somewhere, because the this energy versus position graph has to be continuous, right? So similarly, these two would meet somewhere, these two would meet somewhere, and these two would meet somewhere. Okay, so that is the situation of how the potential, electrostatic potential, experienced by a moving electron moving inside a solid would look like. Okay, so this is called a potential well diagram. Okay, where the wells are exactly these points where this would meet. Okay, for example, let's say if this were to meet here, it would form some kind of well here, right? That's why it's called a potential well diagram. And similarly, there are wells. So basically, wells represent the most stable configuration state. Okay, most stable configuration. For example, if that uh, moving electron, let's say this red marker is now the moving electron, once it reaches here, okay, it's basically stuck to the core, stuck to the positive core. So that's its most stable configuration. And when it's in the in between space, that configuration, we see that it would like to be either here or either here, right? And similarly, in this space, it would like to attract to one of the two positive cores. And as long as it's moving around, its potential corresponding to that position, the potential energy is higher. The least potential energy represents the most stability, right? And similarly here. Okay, so now what happens because of anisotropy is that this potential or this periodic potential has different periodicity in different directions, right? And that is how we can encode this anisotropy information into the models, right? Because the potential itself is different in different directions because of the different positioning. And so to make the situation a little easier, what we can do is we can replace this arrangement, the same arrangement. So we have PE on one side and we have position on one side. So what we said was what we care about the most in this plot is two things basically. First, the nature of the plot, not the exact values. Okay, so the nature of the plot here is that it has several wells and the wells correspond to the positions of the ionic cores. Okay, that's the nature, the qualitative description of the graph. The second thing is periodicity. Okay, this periodicity, it is set by the packaging of the material. Okay, so now what we would do is we will transform this potential into a similar potential which has all these qualitative features, but quantitatively it would be a little different, and we do this for the ease of calculation. Okay, so what we will do is we will assume a square potential as an approximation to this potential. right? So this kind of potential we will assume. Maybe my drawing wasn't the best, but you can understand what I'm trying to say. That these all of these are symmetric, right? They are of same shape, and this we take as an approximation to this potential well, okay? Because we do not know what the exact curvature of these curves is, to put it simply, right? So we will assume that this kind of a square potential, it's called a square potential, okay? Because we only have straight lines here, so we'll take this square potential, and qualitatively it should give us we should be able to identify and explain the difference in behaviors in different directions of the solid, okay? And there are some features of this potential that I have assumed. The first of which is, so there are several regions, right? So first region is this region, because on the x-axis we have position, okay? So first region is this region where the potential energy of the system is 0, okay? Now if we go back to this plot and we see, we argued that when this electron starts from infinity and starts approaching this system, its potential energy is 0 at the infinity, and as it starts approaching, the potential energy grows negative. Now in this version of this model, this potential well, what we assume is there is some distance up to which the effect, the electron does not feel the effect of this charge distribution, okay? So we take some finite length or finite region in which the effect of this charge distribution can be felt, and once the electron has escaped this radius, this particular distance, we say that the electron is free, it's moving freely, okay? So this region, it corresponds to the free motion of electrons, okay? And by free I mean the uh, so I will write the positive charges not felt, okay? So when electron is sufficiently away from the material, it does not feel the effect of these positive cores, and we will call that configuration or that region as the free electrons. Those electrons will be the free electrons, okay? So that's region 1. The second, so similarly this region is also present here on this side, okay? Now there is second region inside this material, which is from here to here, okay? And this is the region in which some effect is felt, okay? Some effect of positive charge is felt, okay? And if some effect of positive charge is felt, it means that these electrons, they get confined, okay? They get confined within these positions, right? Because inside these positions they can interact with these charges, right? If they leave this region, they do not interact with the charges at all. So if they have to interact with these charges, they have to be in this region, and in this region we call them almost free electrons, okay? Yeah, I should. Right? So inside this region we call them almost free electrons, okay? Then there's a third region, right? Third region of electrons is this, which are tightly bound to the electron core, to the positive core, right? So this would correspond to, for example, say the inertial electrons present at any atom, right, which do not take place in the electrical conduction or the thermal conductivity, right? So these are the electrons which are responsible for that, and these are called tightly bound electrons. Okay, so we can identify these three regimes in the potential energy well corresponding to anisotropic solids, right? And one more thing about so one more thing about this distribution is, so let me draw it here, the concept of Fermi energy. So what happens now is that inertial electrons are present here, 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 and similarly in every other well. In every other energy well, there will be the electrons would be filled, right? But once we start filling in the free electrons of a system, we have to start from this level. Okay, this system upward, or this level, this energy level upward, we have to start filling the free electrons of the system. So at some energy level, let's say this one, we will reach the Fermi energy. Right? So this would be Fermi energy. Right? At absolute zero, the energy level, the highest occupied energy level, that is the Fermi energy level. So that would lie in this region, because it will not be, let's say, Fermi energy is not such that the electrons present inside it do not feel the effect of positive ions at all, right? So Fermi energy, we have seen the plots. The Fermi energy, it interacts with the positive core of the, or the electrons present inside the Fermi energy, they interact with the positive core, although mildly, not as strongly as the tightly bound electrons. Okay, so Fermi energy has to be in this region, and it cannot be outside the region of influence of positive ions. Okay, so this is about it. Now, so what is the takeaway from this discussion? The takeaway is confinement due to potential. Okay, right? Whenever electrons are confined or placed in potential wells, they get confined, right? So for example, the electrons here in this well, they are confined to this region only, while the ones in this well, if you consider this whole thing as a well, right, the electrons are confined to this region. Okay, so the takeaway is that there's confinement which happens due to the potential wells, I should say, not just potential. The confinement of electron happens due to the potential well structure of the energy. Okay, that is one. Now the second thing, which we have not done yet but I am about to show you, is that this confinement leads to quantization of energy. Okay, once we confine an electron, okay, it's not possible that this electron can have any arbitrary energy. There are certain levels of energy that it can possess, and this happens because of confinement. Okay, that is what I am going to show now. So before that, let's see. Have a look at a picture which we are more comfortable with. Okay, and this is the situation of waves on a string. Right, waves on a string. So if there is a string which is connected just at one end, okay, it's fixed here rigidly, and let's say this is free to do whatever we want it to do. Now what will happen if so the question is, so this string is not confined to anything, right? So this support here at the left end, it does not mean confinement. It just prevents the rigid motion of this string, right? Otherwise the string can just move in this configuration itself, right? For example, if this string is here, there is no difference between this string and this string, right? This string and this string, it has only translated by some amount, and there is no change in the internal structure of the string, right? So these are same configurations. To prevent that, we have added one fixture, right? But it does not constrain the motion of this string. So now the question is, what shape or shapes can this string adopt? Right? And the answer is any shape. We can give it whatever shape we want because it's not confined, right? So now this word shape that we have used here, by this shape I mean wavelength, right? Because finally whatever the shape of the string is, that shape can be decomposed into sines and cosines, and every sine and cosine function will have some wavelength, right? So it's that wavelength we are talking about, and this wavelength actually gives a certain shape to the string, right? So for example, let's take the example again, same example. If we have a string here, we could give it this shape. Let's say this length of string is L, okay? If this length is L, I can arrange this L length string in this way. I can arrange it in this way, maybe this way. Okay, I can arrange it in this way. I can arrange it in this way, right? So what are these different segments? These are all of length L. Okay, this is the different ways in which I am arranging the spring. But in the first case, this corresponds to a sinusoidal motion which has a wavelength this large, right? In second case, maybe it corresponds to a sinusoidal motion with a lesser wavelength, and in the third case it's even lesser, right? And in the fourth case it's the least of all, right? So this wavelength can be made into shape of any wavelength, right? So that is the observation here. Okay, now I'm going to take the same string and I'm going to confine it on two ends. Let's look at a confined string. So now if I take the same string and confine it on both ends, and I ask the same question again. What shapes, or now in this case I will directly write wavelengths, because we have seen that wavelength corresponds to shape and vice versa, right? So what wavelengths can this string support? Right? So in the earlier case, answer was any shape. Does that answer change for this situation? Yes, it will change. So what happens is the string is fixed at the two ends, right? It's fixed and fixed. So these two will always be the nodes of the wave shape. Okay, so nodes are points of no displacement, right? Points of zero displacement. And if these two supports, or these two ends of the string, if they are fixed, then these correspond to the nodes. Okay, so we will always have a node here, and we will always have a node here at the two fixed ends, right? And what about antinodes? Now we can distribute these antinodes in between this length. Okay, so we can have something like this, right? We can have something like oh no, should be only one, right? We can have this shape, we can have this shape, and then we can have higher harmonics, right? We can have this shape, right? And similarly, we can have higher and higher harmonics. So if this distance between these 2 points is L, okay, so now before making this remark, I would like to explain that in the earlier case, the full wave cycle would have been this, right? So the blue cycle, which is the first fundamental mode of the string, that has a wavelength of 2L, right? And if we look at the red one would have come here, and that is its 2 full cycles, okay? And the pink one, is complete, right? The pink one, just a minute. Yeah, so pink one has completed 1 full cycle, okay? And the red one, that that will complete 1 more cycle, that will complete 2 cycles after this quarter propagation, okay? So in the first case, if we look at the wavelength, okay, lambda wavelength, in the first case this wavelength is 2L, okay? In the second case, the wavelength is L. In the third case, this wavelength is 2 by 3L. Am I making a mistake, or sorry, it will be 4L by 3. No, the wavelength, right? Yes, it would be 2 by 3L. Okay. So these are the kind of wavelengths that this new string can support once we confine it. Okay. Now in the first case, it would have supported any wavelength, right? But now it is supporting wavelength which are some integral multiples or non some fractions of L, some multiples of L. Okay. For example, between this 2L and L, it cannot support, let's say, 1.5L. Okay, it will only support either 2L or L. Now what has happened is this wavelength has been quantized. Earlier it was continuous, but because we confined the string, it got quantized. Quantized means it can only take on some discrete values. Okay, and if we look at, try to derive an expression here, what we find is that what would be the expression here? So this would mean that n lambda, if n is the mode, fundamental mode, then n lambda would have to be equal to 2L, right? Or lambda is equal to 2L by n. Yes. So this is the expression. Okay. And you can see when we had the first mode, in the first mode n was 1, so this is 2L. In the second mode n is 2, so lambda is equal to L, and similarly for third and fourth there will be many higher modes as well. Okay, so this wavelength has now been quantized, and this is because we have confined it. Okay, so the same thing actually happens for the electron as well. Now if we define this electron as a wave function, okay, as a quantum mechanical particle having a wave function, then its energy will get quantized. Okay, so let's see how that works. Now before doing that, let me just make one thing clear. Okay, this is fine. Okay, so just before painting the quantum mechanical picture, there are a few expressions that I want to write from quantum mechanics. Okay, recalling quantum mechanics. So first, from de Broglie's hypothesis, we had that lambda is equal to h over p, right? And then we also know that E is equal to half of mv square. So that is equal to, if I multiply and divide by m, this is m square v square divided by m, right? So energy in terms of the momentum can be written as p square by 2m, right? And if energy is p square by 2m, then we can use this expression here, the de Broglie's hypothesis. Then I can write E is equal to, P can be written as h by lambda, right? So it will be h square divided by lambda square, or 2m lambda square. Okay, and now if we try to introduce this reduced Planck's constant, which is nothing but h by 2 pi, and a wave number. Okay, wave number is k. Usually it's written like this, but in terms of in one single dimension we omit this k. Okay, but this k would be equal to 2 pi by lambda. Now if we introduce these two, then we can write that E is equal to Okay, so we have to fit them in here. We can write 4 pi square h cross square divided by 2m, and instead of lambda you write instead of lambda you write 4 pi square k square. No, it's divided by k square. Okay, so the expression for energy simplifies to h square k square by 2m. Right, so where k is the wave number. Wave number is the reciprocal of wavelength. Okay, and a factor of 2 pi comes in. So what it tells us is that energy is a function of the wave number, right? And if this wave number is continuous, like in the case of a free string, right, fixed just at one end, okay, in that case the energy can be continuous. But once we confine this string, the wave number becomes discrete. Okay, so the energies corresponding to this wave number also become discrete. Okay, so can we do further simplification? Okay, for now we should be fine with this. So but now let's revisit the Schrodinger's wave equation. Right, so what does this equation say? Says that minus h cross squared by 2m d square, because there is single dimension, and I am writing the time independent Schrodinger's equation, okay, not the time dependent part. Okay, and I should probably write here time independent. Okay, so this equation, if we try to solve it for this electron which is confined in a potential well, okay, and the situation that we are going to treat is something like this. Let's say this is potential and we have position. Sorry, so we will assume some confining region. Okay, let's say 0 to, let's say A. Okay, let's say that my electron is confined in this region. Now here I am treating A as some parameter. Later I can equate this A to, I can treat this A to be either this distance, okay, or this distance, because in both cases I have confinement. Okay, so I will derive a general expression, then I can treat this, the same results I can interpret for this as well as this region, because both are confined, right? So for this confinement region, so how do I impose this confinement? So this confinement is guaranteed if the potential outside of this region is infinite. Okay, if the potential is infinite, it means that the electron cannot, because it will need an infinite amount of energy to jump this potential, right? Because energy would be q times potential, right? If q is the charge of electron, which is E, which we know. E times V is infinite. So it needs infinite amount of energy to get out of this energy well, right? So that's why it is always confined, because infinite energy is not realizable. So that's an impossible event, right? So it gets confined in the region from 0 to A. So now I solve my Schrodinger's equation for this case, and I assume that V is 0 here. Okay, inside this region potential is 0, and inside this is infinite. Okay, and what this means is that it can be present anywhere inside this region. There is no preference in terms of it being present at one location or another location. Okay, so if I try to solve this equation inside the box, so this is called a 1D box. Okay, the region from 0 to A. So solve from 0 to A. Okay, and what we find is that since V is 0, this becomes a very simple equation, that the second derivative of psi is equal to E psi, where E is the energy of this electron. Okay, and if we rearrange the terms a little bit, we find that the second derivative of psi x should be E or 2me divided by h cross squared psi of x. Okay, so this is a simple ODE, ordinary differential equation, and we know that the solution to psi of x, it can be written either in the exponential form or the trigonometric form. So it would be a sine kx plus b cos kx. Okay, this is the general solution where we need to figure out what a is. A and b, these constants we need to figure out, and we can figure them out from boundary conditions. Okay, so boundary conditions say that psi of 0 should be 0, right? Because the wave function should be 0 here, because outside this region I cannot find the electron, so the wave function should collapse here at 0, and similarly it should collapse at A as well. Okay, so psi of 0 should be 0 and psi of A should be 0. These are the boundary conditions. So if I put x equal to 0, then what I get is 0 is equal to sine 0 is 0, I get b cos kx. Right? So that means kx should be, when is cos 0? Cos function is 0 when the argument is odd pi, right? Cos pi by 2 is 0, cos 3 pi by 2 is 0. When it is odd pi, that time the cos function becomes 0. So here the solution to this equation is kx is equal to 2n plus 1 pi by 2. Right? Where n can be 0, 1 and so on. So it should be an odd pi. Okay, and actually it should be plus minus. In both cases you will get odd pi. Okay, so then what we get here is just a moment. Did I make a mistake? Oh, sorry. X is 0, right? I am substituting x 0 here. So cos 0 is 1. So when I substitute this, I get cos, there will be no cos because cos 0 is 1. This would mean that b is equal to 0, right? And from here, what I get is 0 is equal to a sine ax, sorry, ka, right? So ka should be plus minus n pi, because sine is 0 when the angle is any multiple of pi. Okay, so this is the condition. Ka should be n pi. Okay, now k would be what? K would be equal to plus minus n pi over a. Okay, so the wave vector can take discrete multiples of pi by a. K cannot be continuous, right? So now if we again look at this expression, okay, and if I take the double derivative of this wave function here, if I take the double derivative, what I get is that psi of x d square psi of x upon dx square, the double derivative is equal to k square times minus k square times a sine kx plus b cos kx, right? This can be easily verified. So that means this whole, so there was a minus here as well, right? From this expression we transpose this to here. So since this psi, this form of psi satisfies this wave equation, what we can write is that these two coefficients should be equal, right? This should be equal to minus k square, okay, and which implies E should be equal to h square, h cross square, k square divided by 2m. So this is what we obtained earlier as well when we uh, before we started solving this wave function. Okay, and now we know what the values of k are, right? K has these values, so we can put the value of k square here, and what we find is E is equal to h cross squared, and instead of k square I'll write n square pi square divided by 2m a square. Okay, so we see that the energy is quantized now. Okay, this electron cannot take any value of energy. It can take value of energy which depends on this quantum number n, right? This is actually what will be the principal quantum number for this electron, right? So with increasing value of n, the energy increases, right? And this is discrete, it's not a continuous energy. And if we plot it as a function of wave vector, okay, if we plot E as a function of wave vector, so let me plot E here and K here, what I get is a parabolic energy variation. Right? Now where now this is dashed, because it means that the energy is not uh, continuously varying with k. There are discrete values of k. K can take on discrete values for which we have discrete values of energy. Okay. So any general k here, it would be of the form n pi by a. Okay. This would be n pi by a for some n, and the energy corresponding to that would be this. Okay, let me call this En, and this would be En for this energy. Right. So this is the effect of quantization, confinement. Okay, confinement leads to quantization. So we have seen two things here. The first thing is potential wells lead to confinement. Okay, and second thing, confinement in turn leads to quantization. Okay, so the first thing here, the first point, that potential wells lead to confinement, it was necessary to include somehow the description of different packing in different directions of a solid, right? So this is going to tell us about the asymmetry or the anisotropy of the solid. And the second point is a consequence, an unavoidable consequence, that the energy gets quantized whenever we confine a so basically a confined quantum mechanical particle cannot take any random value of energy. Okay, that is the takeaway. And using these two principles, now we will try to uh, include some modifications in the root model, which can account for the anisotropic behavior. Okay, so I think that I will do in the next lecture. If there are any questions, please ask. Any questions related to current topic or even the topics before that? So one more thing I want to say is the TA sessions will be on Sundays instead of Saturdays. It will be on Sundays for the next 3 weeks, including today. So today is 7th. The next TA session will be on 14th, and after that it will be on 21st. Okay, and after 21st, it will be as per the original schedule. It will be on Saturdays. Okay. So I am traveling, because of which I cannot conduct the sessions as per the scheduled timings for the next 3 weeks. So if there are any questions, you can ask. We can try to solve a small problem in some. We have got few 2-3 minutes left. Okay, these are mostly descriptive problems. Okay, let's take any one problem and see. So this is a conceptual question, right? So let's try to solve one conceptual question. So the question is, larger the work function, of a metallic rod so the options are higher is the value of Fermi energy, okay, B, no impact on Fermi energy, option C, lower is the value of Fermi energy, and option D, none of these. Okay, so which one is the correct option here? So the question asks us, how does the work
Option
yeah,
option C.
option C, lower is the value of Fermi energy, larger the work function. Yes, yes, that is correct. So if we look at the plot, let me redraw it. Oh no, I'm not going to redraw it. So this here, right? Let me copy it, and because I have to upload the notes. So this is the diagram associated with this. Okay, and here the Fermi energy of this particular system is, so if this is the Fermi energy shown in pink, right, this is the Fermi energy level, then the work function needed would be this much. Sorry, right, this is the work function. Is that right, Antho?
Yes, sir.
Yes. So if we see that, so now let's see what the question asks us is, larger the work function of a material. Okay, so if this work function is larger, larger means okay, so now we have to define what larger means, because the answer may vary in two situations. Okay, larger, if we are implying by larger that it's closer to zero, okay, this work function or this Fermi energy is closer to zero, if that we are counting that as higher, because generally this axis is negative, right, this axis is negative. So if the Fermi energy is large in sign, okay, then it is closer to zero. In that case, work function will be very low, right? But if the Fermi energy is larger in terms of magnitude, that means it's far off from the zero line, the reference line. In that case, work function will be very large. Okay, for this problem, let's see. So yeah, that is the interpretation that has been taken. Okay, larger work function means that it's further away from the zero reference line. In that case, the Fermi energy is lower. So it's lower in terms of its signed value. Okay, not the absolute value. Okay, so I'm going to take this option because it's correct. And the note is, the important point to note here is energy is not measured by absolute value here. Okay, energy is not measured by the absolute value here. So when we say lower energy, minus 10 is lower than minus 5. Okay, we don't have to take the absolute value. Okay, so with that, I'll like to end this session. I'll see you all next Sunday. Thank you.